Okay, welcome to a live session for the Astronomy Online classes. My name is Chris Impey, your instructor, ready to take your questions on any topic.
So the first question is from email, and the person asks, what is the age of the Earth, and how do we know what the age of the Earth is?
The Earth is 4.54 billion years old, and the error on that is actually in that second decimal digit. So the precision of that measurement is something like 1%, which is pretty impressive. We know that because of the age of the oldest rocks determined by radioactive dating. Now, it's actually difficult to find the oldest rocks on the Earth. If you walk anywhere on the Earth's surface on any of the continents, I think if you pick up an average rock, it's a couple of 100 million years old, which is less than 10% of the age of the Earth, because the Earth, of course, is a highly active planet, geologically active, with a lot of erosion, deposition. So rocks are cycling through the Earth and being dissolved and eroded all the time. So the odds of finding a rock that has survived from the beginning of the planet are very low. It turns out there's only a handful of places on the Earth where it's possible to find rocks from what's called the Archean era. The Archean era is the one from 4.5 to 3.8 billion years ago. So that old crust of the Earth is extremely rare because most crust has been eroded or subsumed into the Earth. Those locations where the oldest rocks are found tend to be Western Australia, some parts of South Africa, and Greenland. And that's where people concentrate their effort on looking for the oldest rocks on Earth. The way you measure the age of a rock is by looking for the radioactive isotopes that have very long decay times with half-lives of billions of years, understanding what the initial relative composition of the radioactive isotope and its daughter, the thing that it decays into, would be, and then seeing what fraction of the parent and daughter are in a particular rock. That essentially gives you an age based on the radioactive half-life. And in fact, you can do that not using just one radioactive decay process or chain, but multiple chains to sort of cross-check the method. This method is pretty well established and reliable. The trick is you're only measuring the time since the rock was last fixed in place. If the rock dissolves or reforms or is in a metamorphic state, then then it's not a reliable age estimate. So this has to be unaltered rock. The oldest rock by actual measurement is a tiny little zircon crystal that was found about 12 years ago, I think. Western Australia, it's 4.404 billion years old. So that's not actually going back to the very beginning. The projection of the true origin age involves a little bit of an extrapolation from to the very earliest through the last 100 million years, because we can't actually find rock left over from the moment where the planet finally congealed. But we can get pretty close to that and then extrapolate a small formation time. The cross-check on that, of course, is from lunar rocks. The Earth and the Moon essentially formed close to the same time, the Moon forming from an impact on the Earth by a Mars-like object, something like 50 million years after the formation of the Earth. The Moon rocks, of course, are almost completely unaltered since then because there's no geological activity on the Moon. So Moon samples from Apollo have been used to confirm the age of the Earth-Moon system. So the result of all that is a very reliable age measurement of the Earth. And of course, that essentially corresponds to the age of the Sun as well, since we think that the Sun and all the planets formed in a relatively short period of time. The planet building process probably took 10 or 15 million years, which is a very small fraction of the age.
All right, the next question is from a live viewer who asks, as an astronomer, you've probably seen it all, or at least most of it. Do you still like to just look up and see all those billions of stars in the macro sense rather than from a scientific viewpoint?
Yeah, it's a good question. Yes, I think astronomers always maintain a love of the sky and the aesthetics of the sky. Tucson's a city now with a lot of lights, although we have an ordinance that has limited the contamination and brightness of the night sky. So I've spent most of my life in cities, in fact, and I have to go elsewhere to see the beautiful night sky. Some people live in rural areas or in remote areas and they just get to see it every night. So I have to go somewhere to see it. My favorite night skies are historically from Mauna Kea in Hawaii, where I was a postdoc, and I've been a number of times since. But actually, when you're on Mauna Kea, you're mostly up at altitude. At the summit of 14,000 feet, your eyes are oxygen starved, so your night vision is much poorer than it would be at sea level. Probably the best sky that I've seen routinely over the years is from Chile, from our observatory in Chile at Las Campanas, and Cerro, the sister observatory not far away, and the European Southern Observatory. These three sites are all about 8,000 or 9,000 feet high, so that's not so high that your eyes are oxygen starved. But Chile is dark, pristine sky, really uncontaminated by pollution or city lights. And so, you know, I don't get there that often, of course, but the skies there are so spectacular, they sort of remind you of the time before humans were around, sort of messing up the planet with their pollution and their light.
Right, the next question is, what are your views on combating pseudoscience in the modern world?
It's a big issue for most scientists, and it's becoming more of an issue, I think, because we're in an area of, you know, supposedly pseudo facts or fake facts or facts masquerading as truth. So scientists have a pretty clear idea of what constitutes evidence. It has to be information that can be validated or verified by anyone, not just a scientist, in fact. Information that's shared and publicly available, so no hidden information or secret knowledge that, you know, only certain people have. And information that the veracity of which is confirmed by standard methods. You know, they could be statistical or mathematical, just sort of quantitative ways of understanding whether an assertion is true or not. So scientists pretty much all hold to that standard for evidence and for information. But out there in the real world, in the everyday world of socio-cultural issues and politics, the same standards don't always apply. People make assertions or hold beliefs or state things as fact that aren't necessarily facts. And that dialogue, you know, that can be a rich dialogue, of course, but it can be littered with erroneous information. So, you know, my view is that just in my experience, pseudoscience and false information is sort of on the rise, and people are often quite vigorous about promoting false information for their own reasons. So pretty much it's incumbent upon, I think, all professional scientists to do their part for combating pseudoscience or false information with, you know, correct information, with the real scientific information, or, you know, playing the role of skeptics and asking, well, why do you believe that? Or what's your evidence for believing that? And it has to be done gently. You can't confront people about their beliefs and things they hold true, which might be held emotionally true rather than logically true. And that's a tricky area when you're combating that. But I think with sort of gentle persuasion and sort of a logical approach, that's something we all sort of need to do more of.
All right, the next question is, I was wondering, in what way is the work done on the International Space Station helping us learn more?
The International Space Station, people tend to forget about it. It's been going for, you know, it started building 25 years ago, but it's been pretty much fully built for 15 or 17 years. And it's been continuously occupied by astronauts from a variety of nations, I think 24 nations, since then. So people sort of forget about the existence of it. It's a very large, it's the most amazing, large, complex structure that humans have ever built off the Earth's surface, of course. And it's used for science, it's used for research, it's used to learn about the effects of zero gravity and the space environment on humans, because there are occasional situations where astronauts have spent more than a year consecutively on the space station. One of the Kelly brothers, the twins, American astronauts, of course, famously spent a year up there while his twin brother was on the Earth, therefore forming a little miniature scientific experiment of the effects of zero gravity. I think a Russian cosmonaut has the record at something like 826 days in orbit. So that's one of the most important things a space station has done, is give us research evidence on the effects of the space environment on humans if we ever left the planet fully or did very long voyages through the solar system. It's also used for science. Obviously, zero gravity is an environment where you can, you can look at the effects of sort of what's called microgravity, situations where gravity essentially doesn't exist, and say you want to study, how chemicals react or how capillary action happens in a living organism, or how cells operate in zero gravity. There's a whole set of science experiments that have been done on the space station. I would say they've not been transformative. They've not been, profound. And I'm not sure you would want to fund something expensive like the space station just for its scientific research. So people, scientists and technical people have been a little skeptical of the value of the space station. I think in the end, the value of the space station has been to demonstrate international cooperation in space, because even with the Russians and the Chinese, who are, we've had our issues with the Russians and the Chinese geopolitically, and even in the space arena, we have worked with them, especially the Russians, very harmoniously on the space station for 2 decades, or regardless of whatever the politics of the Earth are. So it's in that sense, it's a noble experiment. It was also built by an international team. So different components of the space station were designed independently and then slotted together. And that has proved to be a successful collaboration. Now, the space station is under some threat. There's a funding threat to it to keep it going. There's the issue that it's slowly degrading in its orbit, and then without active intervention, it will deorbit. It will eventually just fall into the Earth's atmosphere and burn up into small pieces. So it's actually going to take money and action for the space station to persist for another decade. The Chinese have also revealed plans to build their own space station, so there might be competition to the space station. And if the International Space Station deorbits or is not given more funding, then the Chinese may have the only game in town. So there's decisions approaching for the space station that will determine its future.
All right, the next question is, can you explain what the Lagrange points are and why it is ideal to send spacecraft there?
So Louis Lagrange was a French mathematician and celestial mechanics expert from, I think, the mid-19th century. Very brilliant mathematician for the most part. And he developed the orbital calculation that demonstrated that there are both stable and unstable gravitational balance points in a system of objects orbiting each other. So this is true, for instance, in the Earth-Moon system. It's also true in the Earth-Sun system. And these points are numbered, 1 through 4 typically. So there are 2 Lagrange points that are on opposite sides of the Earth, that are on the opposite side of the Earth to the Sun and inside the Earth from the Sun. And then there are Lagrange points to the side of the Earth in its orbit. And these are only one of these, 2 of these Lagrange points are stable, where an object can sit there and be in gravitational balance. The others are unstable, and so the object will tend to drift away from this gravitational balance point. So the advantage of that is it's a way to keep an object remote from the Earth, about a million miles from the Earth in the Earth-Moon system Lagrange points, with very minimal expenditure of rocket fuel. So you can keep something remote from the Earth in a sort of gravitational equilibrium with a tiny amount of retro fuel energy from a rocket. And so that makes it a very attractive location for a satellite, where you want something to be remote from the Earth, remote from interference of radio waves or light pollution from the Earth, and yet in a stable location where it can look at the rest of the sky. So there are a number of space missions there. James Webb Space Telescope is destined for one of these Lagrange points, and there's probably something like 6 or 8 different other space missions and astronomy missions that use the Lagrange points.
All right, the next question is from a live viewer who asks, can you please discuss the significance of the TRAPPIST-1 exoplanets, and can we expect to find exoplanets like these closer to Earth?
So the TRAPPIST planets are really important. They represent terrestrial planets, Earth-like planets, found around a red dwarf star. So that's really what's most interesting about them, because there have been Earth-like planets found. There are several hundred planets within a factor of 2 of the Earth in either size or mass. And most of those are around sun-like stars, which is where most of the exoplanet hunting has been done. But there are dozens, perhaps 100 red dwarf stars for every star like the sun. And so to find multiple Earth-like planets around a single red dwarf star, when there are so many red dwarf stars in the Milky Way, it ups the number of terrestrial and potentially habitable planets in the Milky Way by over an order of magnitude, perhaps 2 orders of magnitude. So it's an extraordinary discovery. Of course, you can't extrapolate based on a sample of 1, however good that sample is. But other work is underway to look at bigger samples of planets around red dwarf stars. So having found this very rich system around a single red dwarf, it's very likely that there are more. These planets, of course, are in very unfamiliar orbits. They orbit the red dwarf to be habitable around a dim star. Of course, they have to be very close to that star. So whereas Mercury orbits the sun in about 3 months, some of these planets orbit their star every few days, and the rest a few weeks. So these are super close, super rapidly orbiting planets. Because they're so close to their star, they're tidally locked, which means they always have one face pointing to the star, as opposed to the Earth, where the Earth rotates as it orbits the sun. What that does to their habitability is not yet clear. If they have atmospheres, and we don't know about their atmospheres, it's likely that the atmospheres will sort of spread the sun, the star's energy across the face of the planet, even when it's not spinning as it orbits the red dwarf. But that's a speculation. We simply don't know. The distance of this system from the Earth is about 10 times the distance to the nearest star, Proxima Centauri system. But that's still relatively near. That's in our backyard. So having found such a rich system in our backyard around a very ubiquitous type of star in the Milky Way is a very exciting signpost for exoplanet research to come.
All right, the next question is, a few days ago, NASA's SWIFT spacecraft mapped a star going into a black hole. Was anything new learned about black holes?
Yes, these events are important because they're dynamic, real-time events that teach us about black holes. So SWIFT is a telescope that's designed to look for transient signals in the sky. It looks for high energy emission and also optical emission from the sky. It was typically designed to look for the afterglow from gamma ray bursts. A gamma ray burst is probably not a single phenomenon, but these are stellar cataclysms, possibly the detonation of a massive star that leads to the formation of a black hole, where for an instant, literally a second or a fraction of a second, this object, this detonating object, outshines the rest of the universe in gamma rays. So SWIFT has been designed to follow up these objects, and as SWIFT has had time, to study different kinds of transient phenomena, it's been realized that SWIFT has the ability to look at these occasional times when a black hole ingests a star whole. Most black hole accretion, most of the situations where black holes are gathering matter into an accretion disk and then swallowing it, it's kind of a smooth situation. So the accretion disk is smooth gas, perhaps gas that fell in slowly, or stars that were ripped apart and turned into a smooth disk of matter. And so that energy and gravitational energy is dropped onto the black hole slowly. But every now and then, a star could be orbiting near a black hole and be pulled into its orbit or ripped apart or swallowed whole. And so SWIFT has seen not just one, but actually a number of these events, I think a couple of dozen over the years. It's really difficult to interpret the information because all SWIFT does is it shows a sort of light or high energy radiation trace of the event, energy over time, and you have to sort of infer what was going on. These are systems that are so far away, typically hundreds of light years away, that there's no, even though SWIFT has an optical telescope on board, it can't take a picture of the system, so it can't actually watch a star be devoured or fall into a black hole. You're having to infer what's happening from the way the energy is released in a transient way. So there's a fair amount of speculation and interpretation attached to this. But Swift has contributed substantially to this subject, and it shows that black holes do ingest matter in this way. They do occasionally swallow stars whole, or at the very least, the star is torn apart as it reaches the event horizon.
Our next question comes from a live viewer who says, I'm going to the Atacama Desert. What is the best time of year to go there for stargazing? Can I observe at one of the big observatories located in the Atacama?
So the Atacama Desert in the northern part of Chile is home to a number of major observatories. It's home to the European Southern Observatories, BLT. That's 4 8-meter telescopes that work as one, as an interferometer, or independently observing their own targets in the sky. It's also home to a high plateau up at 16,000 feet, very high up, where I visited last year actually with a college group, sort of donor group from the College of Science here. And on that site is the ALMA array, the Atacama Large Millimeter Array, and also a number of individual radio telescopes. So those are the two sort of primo astronomical sites in the Atacama Desert, the 4 large optical telescopes of the European Southern Observatory, and these large set of radio facilities at the ALMA site. There is no bad time of year to go to the Atacama Desert. It is one of the driest places on Earth. There are locations where it hasn't rained in recorded history, or at least for a century. So it doesn't have a rainy season and a dry season. And the variation of summer to winter is modest. And you're mostly at high altitude anyway, so it can even be cold in the sort of southern hemisphere summer at altitude. So it's really pretty good to go anytime. If you want to avoid the crowds from the Chileans, then you'll avoid their peak holiday season, which is January and February. So those are probably the only months to avoid, just because it kind of crowded with locals. Otherwise, it's a great place to go. In terms of seeing these facilities, it's tricky. You have to make an arrangement. They're not just places you can just drive up to. The easier of the places to visit is the European Southern Observatory site. Paranal is the name of this mountaintop, and that can be done. They have public tours of it. The ALMA site is harder because of its altitude, because it's sort of dangerous to be up there. You can actually have altitude sickness problems, substantial altitude sickness problems. They have a base camp, a base facility where you can actually learn a lot about the facilities and their videos and their instruments you can visit. So the grounds, the base camp of ALMA is easy to visit, and the public can go there. But generally, people who just show up are not allowed to go to the high ALMA site. So pretty much your only way of going to the high ALMA site, the top, is with a staff scientist by prior arrangement. So if you just turn up, you're unlikely to be able to go up there. But there are wonderful places to go. There's also, most people stay in San Pedro de Atacama, which is a little desert oasis town, has sort of ecotourism. You can visit the salt flats, or fantastic geological formations. There are active volcanoes or geysers where you can visit at dawn and have your breakfast cooked in the bubbling hot pots from the geysers. So there's a lot of cool things to do there.
All right, the next question is from a live viewer who asks, when a body enters the curved space-time around your object, why does it orbit around it instead of falling completely into that gravity well?
I mean, it's a good question, and it can fall straight in. So it's entirely possible for two objects, for an object approaching a more massive one, to have what's called a plunging orbit, where it's essentially heading directly for the centroid of that object, and so it heads straight in. And if it were a black hole, it would fall straight in to the event horizon at an accelerating rate. But for two objects approaching each other, the odds are that they will not be headed exactly for their centers of mass. And so the most likely trajectory is one that's offset, or a glancing trajectory. And in that case, what's most likely to happen is that the infalling object starts to do a sort of a series of sweeps around the object, be gravitationally retained if the second object is more massive, and will do a series of looping orbits before probably falling in. So it's just a matter of the largeness of space and the smallness of astronomical objects. The two objects are unlikely to approach each other exactly as in a head-on collision, which leads to a more complex orbital situation before the final infall.
All right, the next question is again from a live viewer who asks, can you tell us about the James Webb Space Telescope, and do you have any involvement with that project?
I don't have direct involvement. One of my colleagues, Marcia Ricci, is the PI on one of the 4 instruments on the James Webb, the infrared instrument on James Webb, and so we have a lot of involvement here at Steward Observatory and the University of Arizona. And a lot of us are scientifically interested in what we could do with Marcia's instrument. The James Webb itself is the biggest game in town in astronomy. Its budget now probably $9 billion and counting. It will go up. The launch date is set in October next year, October 2018. And pretty much that's a pretty firm launch date after a number of delays and a lot of cost overruns. All the instruments have been delivered. They've all undergone what they call thermal vac testing, which means those 4 scientific instruments go to NASA centers where they can be put into huge vacuum chambers, taken down to as close to a space vacuum as possible, subjected to ultraviolet and gamma ray, high energy radiation, simulating the space environment. And then also given another set of pretty serious tests that involve shaking them, because they're going to be launched, subject to a lot of G-forces and a lot of vibration. So these instruments have, gone through very rigorous testing. And at the moment, I think the last stage is their integration into the launch package, into the whole thing. Separately from that, at Goddard Space Center, the telescope assembly has been tested. This is a very challenging mission where the size of the telescope, the collecting area is 6.5 meters, but the launch capability cannot hold something of that diameter, so the telescope mirrors will unfold in space. So this telescope will be launched. It will be taken to its remote Lagrange point location where it's not serviceable by astronauts. There's no way it can be fixed once it's launched and deployed. And then all these moving parts will have to work perfectly for the telescope to unfold itself to its full aperture, for the solar rays to unfurl and give it power, without which, again, it would be dead in the water and not be able to do its work, and for all the instruments to go live and start taking data and to go through their test cycle before doing astronomy. So there's going to be a nerve-wracking period of probably 3 months after it's launched before anyone realizes whether the whole thing will work or not. And the cost that it's incurred up to this point, too big to fail, you might say, everyone's a little anxious because it's a very technically challenging project. I think it's more technically challenging than the Hubble Space Telescope was.
All right, our next question is from a live viewer who asks, what is your best tip for teens who are very passionate about astronomy, and at what age did you decide you would become an astronomer?
So I didn't get into astronomy until I was a late teen, so pretty much until I'd gone to college, because I was in the UK and I lived in London, so I didn't have a night sky, not even anywhere near that I could get to. London's a huge sprawling metropolis full of city light, and I got into astronomy through physics, and that's the gateway drug, if you like, or the first path for many astronomers. They do an undergraduate degree in physics and then move to graduate work in astronomy. Now it's possible to do undergraduate degrees in astronomy, so you can get into it more. And there are often high schools that have astronomy courses, and even some middle schools. So it's certainly possible to get your exposure to astronomy earlier and then know that you want to do it sooner. So I got into it, a little later than some people through physics. For if you're at high school or middle school, the obvious 2 answers are to, if there is an astronomy club at your school, if it's big enough to have an astronomy club or just has enough interest, then that's the place to go. There's the people to join, because there undoubtedly will be small telescopes. Hopefully the school can afford a couple or individuals will have them, and you'll go to star parties and viewings. And even if your school doesn't have an astronomy club, it's almost certain that there's an amateur astronomy club in your location, in your town or nearby larger town, because there are hundreds of amateur astronomy clubs all around the country, and down to even some very small places. And those people are always happy to have students, high schoolers or middle school students, come out and hang out with them, go to their star parties, learn with them. And many of the amateur astronomers, some are teachers, a lot are engineers, a lot of people with technical skills, a lot of people who build their own telescopes or know how to build telescopes. So through amateur astronomy clubs, you're going to learn an awful lot about the subject. Apart from learning the sky really well and just doing a lot of star viewing, you'll probably learn a lot of the technical side of astronomy too, because so many of them are technically trained. So those are the two obvious ways. And then, of course, just using the best of what's out there on YouTube and in the world of videos and TV and cable programs, because the best astronomy shows, are really very good. And there's the classic ones like Cosmos and the reboot of Cosmos with Neil deGrasse Tyson, but there are also a lot of one-off specials, Nova, and so on, that give you a lot of background. And then there's magazines. There's Sky and Telescope and Astronomy magazine. That sort of two popular astronomy magazines. They each have circulations of 150 or 200,000 copies. If you don't want to get a subscription, you can probably see a bunch of old copies in a library nearby or in a bookstore that sells used books, and you can get a sense of how to buy your own telescope from the ads that are in those magazines, or get a sense of what astronomers do when they're viewing the sky.
All right, the next question is, I keep hearing more and more rumors of Planet X or Nibiru entering our solar system. Do you have any information?
So the Planet X concept, of a large, as yet undiscovered planet in the solar system, it's a rumor that refuses to go away. So I'll take one aspect of it that I think is true. It's almost certain that there are dwarf planets that rival or exceed Pluto in size that remain to be discovered. So we already have a couple. And the best guess is that when those surveys out in the Kuiper Belt, the Kuiper Belt is the region of space from about 40 to 80 astronomical units, so sort of beyond the orbit of the 8 traditional large planets in the solar system, there are likely to be other large objects out there, bigger than Pluto again, so worthy of our attention. But these are pretty far away. These are very far from the sun. They're very small. They're dim. They're hard to find. It's taking surveys years to fully troll that area of sky. The idea that there could be a large undiscovered planet, especially one that either is very close to the sun or loops in close to the sun periodically, that is a hypothesis that's pretty easy to refute. For example, if there were a planet sort of co-orbiting the sun on the other side of the sun, so we can't see it because the sun's in the way or the sun's blinding light stops us from seeing it, that's fine to hypothesize that, but the gravitational effect of such a large planet so close to the sun would be obvious on the inner planets, simply obvious, and we don't see that. So we can pretty much rule out any sort of hidden, dark, or conveniently behind the sun large planet X. So it simply doesn't exist because our knowledge of the gravity and the inner solar system is so good. An object that similarly would just loop in occasionally into the inner solar system, that would also show its effect on the orbits of the planets, because each time it looped into the inner solar system, it would perturb those orbits, and we could see the effect of that long after the object had looped away and gone to a larger distance and become dark. So the sort of classic big planet X, hidden planet X hypothesis is pretty much refuted at this point.
All right, the next question is from a live viewer who asks, as we know, the Martian surface does not support life, so why has the human colonization of Mars always been at the hub of space talks and interest?
I think it's a good question, because Mars is a challenging place to go. It's a minimum of 8 months, extremely hazardous for humans, extremely hazardous voyage. It's a very inhospitable place for humans to live. and work, and it's very expensive to set up even a simple colony. Even a handful of astronauts there would be tens and probably a couple of $100 billion. So I think the moon has got a little bit of the been there, done that problem, that it's close, that it's a natural place to learn how to live in space, but it's not as glamorous as a location, and it doesn't have the novelty value of going to another planet. That's on one hand. On the other hand, why Mars is more interesting than the moon is because although the surface of Mars is essentially sterilized because the atmosphere is so thin and the UV radiation would really not allow microbial life to exist in the top few centimeters of the soil, the possibility that Mars has life right now under the surface is very strong. We know that there's ample water under the surface of Mars. We know that occasionally it bubbles out onto the surface, and when it's mixed with a lot of salty material, it can even transient or temporarily exist on the surface itself. So there's a lot of water there. In fact, if you took the subsurface ice at the mid-latitudes, which has been shown by radar, and melted it all and smeared it around the planet, it's about 4 centimeters and 1.5 inches of water around the whole planet, which is not a lot of water, but it's pretty impressive that Mars overall is really that wet if that ice were melted. So in some underground situations, that ice will be melted because of pressure, because of radioactive heating from the interior. And so that means that Mars has the possibility of be hosting life right now. And that makes it a very compelling target for humans to explore, because if we want to look for the first example of life beyond Earth, that might be where we find it. And doing that exploration to look for life is probably beyond the capability of the kind of rovers we're sending there. These rovers are very good at roaming around on the surface and picking up surface rocks and maybe digging a few inches or maybe 6 or 8 inches under the surface, but they can't go deep enough to get to a subsurface aquifer where life might be, and they just don't have the capabilities of a human geologist. So for people who want to find life on Mars, really, they think we'll have to go there. People will have to go there to one of the most plausible locations where life still might exist under the ground. And then for living in space and demonstrating our ability to live on another world, Mars is a better bet. It's easier than the moon in the sense that the gravity is closer to the Earth than the moon's gravity. So the stresses on the human body from adjusting to a different gravity situation would be less. The dangers, of course, are correspondingly great because it's so far away.
All right, the next question is from a live viewer who asks, do the number of elements in nature have a limit, or can an indefinite number be created artificially? Is there a limit to the size an atomic nucleus can reach?
There is a practical limit. I mean, the number of stable nucleotides is fixed and it's been the same for decades and decades. However, the number of what's called transuranic elements, or elements beyond uranium in atomic number, has been slowly increasing over time, but they're all unstable. So as for is that number of transuranic elements limited, that's an interesting question. So the several dozen transuranic elements that have been created in physics labs, mostly in the United States and the former Soviet Union, they're done under extreme conditions of pressure and temperature, and those heavy elements, super heavy elements, exist for a fraction of a second before they disintegrate in radioactive decay, very rapid radioactive decay. So they're barely stable nuclei. So you might say it's a semantic issue whether you've really created a new element or not, if that element only exists for a millisecond before it disintegrates. It's now at the point where up at atomic numbers of, I think the atomic numbers are up to the high 120s. So uranium is 92 and you get up to the high 120s, the low 130s, and you're starting to run out of names for these. They tend to be named after famous physicists, these transuranic elements. It is now getting harder and harder to create new ones. I think I only read discoveries of a new one every few years, basically. So there may be a practical limit where the instability of the nucleus is just so great that it just literally falls apart as you create it. And if its transience is like a millisecond or a nanosecond, then I don't think you really can call it an element.
All right, our next question is, if the whole universe is expanding, then the distance between the Earth and the Sun should be increased, right? Does this not counteract gravity?
So the cosmic expansion measured by Hubble in the late 1920s relates to it's alluding to the expansion of space-time. So the space-time continuum itself is expanding and carries objects apart with it. But that space-time expansion applies on large scales. On smaller scales, gravity can overcome that space-time expansion or countermand it to the level where objects are held stably in an orbit. So the solar system is a good example of that. The solar system, the planets in the solar system, even though the solar system exists in an expanding universe, the gravity of the sun operating on the planets is sufficient to hold them in bound orbits, even though on larger scales space-time is expanding. The same for the galaxy. The Milky Way, the sun is in a 240 million year circular orbit of the center of our galaxy, as are all the stars outside it and all the stars inside it, according to Newtonian laws of gravity and in stable orbits, even though on larger scales than the Milky Way, the universe is expanding. So basically, the expansion of the universe does hold cosmically, globally, and on very large scales, but on scales where large numbers of objects can be close together in space, then their mutual gravity can exempt them, if you like, from the cosmic space-time expansion.
Right. The next question is the political climate impacting the space program in any way?
Yes, it's. I think the biggest impact is the uncertainty. So right now in the United States, and some similar things are happening in Europe and other countries, the economic anxiety of the age we live in is leading to uncertainty in what the commitment to science funding is. In the US, it's become a very obvious problem because the budget that the administration has just released has substantial cuts to science, 20% cuts in the National Institute of Health. NASA actually got a slight boost, so NASA has not done badly so far. Nobody really knows what the effect on the National Science Foundation is. That simply hasn't been laid out yet. So it's not really the impact on the budgets, it's sort of the uncertainty, because it makes it very hard to plan scientific projects. It means scientists don't know the likelihood that they'll get their next grant, and so they don't know how to plan collaborations or whether to take on graduate students. So down at the grainy, gritty level of how science is played out one person at a time or a group at a time, this uncertainty is sort of bad. Also, the fact is that the science enterprise does not get substantial investment. The percent of the US GDP that's spent on R&D is, I think, less than 2%, maybe 1.8%. That's actually a pretty low percentage. It's lower than some rivals. It's lower than the Chinese are rapidly growing their R&D, for example. So the science enterprise is not getting the investment that most scientists would like. And the truth is the return on investment from science since the Second World War has been extraordinary. Even the pure sciences, like astronomy itself, have had spin-offs or payoffs into the commercial sector in terms of job creation. So I think the uncertainty of the political climate is a real thing, and it's affecting science. And then the other thing that's affecting science, which was subject of an earlier question, is the fact that the value of data, the value of scientific reasoning and evidence-based reasoning has sort of been degraded in the current political discourse, and that essentially hurts all science.
All right, our next question is, what is de space? Are you familiar with that term?
De space it's not the real universe we live in, but it's a construct emerging from the early speculation of cosmology about 100 years ago. It's essentially empty space. It's how space would expand, how expanding space-time would operate if there were no matter in it, matter-free expanding space-time. And essentially, de Sitter space would, of course, continue to expand, infinitely, or sort of just gradually thin out forever. It's a very artificial construct because we know the universe has stuff in it, mostly dark matter, along with about 1 part in 6 normal protons, neutrons, electrons. But de Sitter space was an important concept when people were trying to solve the equations of general relativity and figure out how space-time should evolve. Because back then, and then we're talking about now the 1920s, general relativity was published in 1916. Willem de Sitter was a contemporary of Einstein, mathematical physicist. I think he was trained as a mathematician. And he was trying to solve Einstein's equations as Einstein was, as Friedman was, as various founders of general relativity were. And so de Sitter space, is an interesting hypothetical for how space-time behaves when there's very little or absent matter. It's essentially the pure functioning of expanding space-time, unmodulated by matter. And so it's an extreme situation. It's an extreme case, a limiting case, if you like, when there's no matter.
All right, the next question is from a live viewer who asks, are there any good places for stargazing in Europe?
Definitely. If you look at one of these world maps at night, it's easy to find online, the world at night, you'll realize that overall and in general, Europe isn't a great place for naked eye astronomy because the population density is so high. Britain, my home country, is just a sea of light, except if you go out into the Highlands in the north of Scotland. So that's one part, of course, the Highlands, north part of Scotland. You pretty much have to go to the peripheries of the continent to find a good dark sky. So the best places to go, of course, are just the lower densities of population. The center part of Europe, Holland, Germany, the northern part of France, northern part of Italy, those are really terrible. There's not many dark skies, but France is a big country. There's some beautiful dark sites in southern France and in the middle part of France. There are definitely parts of Italy that are quite dark, more remote northern parts. And so you just have to look at that map, look at that Europe at night, and you'll see where the best places to do astronomy. Spain also has some very dark locations too. So you have to pick the large countries with relatively modest populations before you can find a dark sky. And it's not going to be a place, for example, like Holland.
So the next question is from a live viewer, and it asks, how much wishful thinking patches up our imagined view of the universe?
That's a good question, because astronomers are not immune from wishful thinking. I would say the area where some people believe there's wishful thinking going on is our sense that we have a final cosmological model, because the standard cosmology has 3 major ingredients. It has normal matter, for protons, neutrons, electrons, that we're all made of, the Earth is made of, the Sun is made of, and that's 4%, roughly 5% of the universe. And then it has dark matter and dark energy, which are by far the majority of the universe. And the evidence for dark energy is based on essentially a single type of observation of accelerating expansion. And the evidence for dark matter is based on more evidence, but we still don't know what dark matter is. So some commentators and some people who are working in the field believe there's some wishful thinking involved in our talking about dark energy and dark matter as if there are things that we understand and that have to be a part of the cosmological model. So, for example, there's a debate that's persisted for decades that insists that a reasonable way to approach the cosmology problem is to consider the fact that Newton's law of gravity might not hold on large scales. Because Newton's law of gravity, the inverse square law, is not actually tested on scales of galaxies. It's only tested on solar system scales where it holds. If Newton's law of gravity is even slightly modified on very large scales, you can do without the need for dark matter at all, this mysterious component that most people think exists, but we've never identified the particle or what it is. So that's an example that could be wishful thinking. We could be using convenient or wishful thinking in persisting in believing in dark matter, when an alternative route to the situation to consider altering our theory of gravity, of Newtonian gravity, well, would do away with the need for dark matter. Dark energy is in a similar category, I suppose, because the evidence for it is still based on one type of observation. There's no physical understanding of the nature of dark energy. And so continuing to believe that something called dark energy exists and there's new physics behind it, we just don't know what it is, that could be wishful thinking too. Perhaps the observation of acceleration is in error, or we're just misinterpreting it. So I think cosmology is in a tricky situation right now. And the longer the situation persists of the two biggest ingredients in the universe being essentially unknown physically and not part of standard physics, then the danger of wishful thinking or of deluding ourselves has to be considered real.
All right, next question is, please discuss how the observable universe is more than twice larger than its age in light years. Doesn't this mean that the galaxies at the edge move at speeds faster than the speed of light?
Yes, it does, and yes, that's part of the standard model. So that's a good question. So to put it in a nutshell, the edge of the observable universe corresponds to a distance, the distance in space, that's almost 3 times the age of the universe in years. So the age of the universe is sort of 13.8 billion years. So you'd imagine that the farthest away anything could be would be 13.8 billion light years, when in fact it's almost 3 times that number. And the reason is because for most of the first third of the universe's history, any 2 points in space were moving away from each other faster than the speed of light. Then they decelerated due to the influence of dark energy, and in the last third of the age of the universe, they've started to move away faster again due to acceleration, we think, caused by dark energy. So if you do the math of the expansion history of the universe with a strong deceleration in the first third, then a sort of coasting phase converting into acceleration in the last few billion years, you infer that those distant galaxies must actually be further away than you would think based on light travel time, because those galaxies were moving away from each other faster than light speed for a good fraction of the history of the universe. So it's actually part of the standard picture of cosmology that is true. The speed limit on the expansion rate is not the same as in special relativity. Special relativity does indeed say that no signals can travel faster than light, but the expansion of space-time in general relativity does not have a speed limit attached to it. General relativity doesn't put a speed limit on the expansion rate of space-time, and in the model of cosmology that we measure and believe, the expansion rate was faster than light for a significant fraction of the history.
And the next question is, if you could make a suggestion to Elon Musk of SpaceX on a future mission, what would it be?
Well, he's imaginative enough that he's probably thought of all the good and smart things to do. He's obviously just in the last year announced his much more ambitious than any of the rockets you're seeing now. I mean, his current work is based on the Falcon Heavy project, of the ability to lift hundreds of tons into low Earth orbit to feed the space station, to fuel current exploration of the moon and eventually Mars. But he released about a year ago a visionary idea of an interplanetary transport system, which could potentially carry hundreds of people, tourists, not just astronauts or scientists, around the solar system to Mars and even to more distant locations. So this is taking his current rocket technology and sort of scaling it up by 2 orders of magnitude, which is pretty amazing stuff. And he obviously isn't anything close to that right now. So he's playing out a future capability that's got to be decades away. So, you know, if I were going to suggest something, I would suggest, you know, he might get into the game of trying to envisage new propulsion systems that could take us to the stars. Breakthrough Starshot has given us one of these ideas, which involves making tiny little robotic spacecraft with solar sails attached and then beaming lasers at them to accelerate them to a few % of the speed of light. Well, maybe Musk, because he's a rocket designer and rocket engine designer, could dust off some of the ideas people have had over the years of how to do an interstellar rocket based on not carrying the fuel with you, but harvesting it from the very thin hydrogen that exists in interplanetary space. So if I were suggesting something for him, it would be sort of a new interstellar propulsion system, prototyping it.
All right, and then the last question for today is, how sure are we that our probes will not contaminate other celestial objects that might have life, and what would count as contamination?
The issue of contamination is a significant one, and NASA takes it very seriously. So NASA has had a policy for over a decade of essentially taking quite stringent precautions to not contaminate an object that is visited by a NASA spacecraft. Some of that happens easily and naturally because the spacecraft either goes through a trajectory that takes it through an atmosphere and essentially blasts off all contaminants, or they're radiated away in the vacuum of space, or maybe in the landing, like on Mars, you can also sterilize a spacecraft as it lands. So NASA's sort of taken the point of view that it doesn't want to contaminate any other astronomical object, in particular Mars, where we think there could be life on Mars, so you don't want to contaminate it with terrestrial microbes. NASA also tries not to contaminate a planet or just litter it with debris that may or may not include microbes from the point of origin on the Earth, clean up after itself, essentially. So this contamination issue is taken very seriously. Of course, the highest stakes of all come when the contamination involves a sample brought back to the Earth. So as NASA gets to the point of bringing back Mars rocks, which is it's a very well-developed plan for sample return from Mars within 20 years, I think NASA will probably achieve that goal because these are well thought out missions and sort of taking it in steps. There's going to be really extreme caution and concern taken to ensure that there are some sample or package delivered to the Earth is not contaminated or not potentially have microbes in it or microbes on it that could be a pathogen as far as terrestrial life goes. That's a real concern. Moon rocks were taken to a place in Johnson Space Center. They were never handled in the air. They were kept in enclosed situations in a vacuum. And at Johnson Space Center, they've lived since the Apollo missions in a situation that's like a level 4 biohazard containment center. That's the kind of place that could handle Lassa fever and all the worst hemorrhagic fevers. So these are pretty secure facilities. So NASA's known how to do this for decades, and a Mars sample will be subject to that same stringent concern. No lab scientist or astronaut will touch the Mars sample in any way. So that's what NASA's trying to do. So I think that's all for today. I'm actually going to encourage people to ask a question that I thought I would get today but didn't, which is about the issues that are going on with the Hubble constant, the expansion rate of the universe. This is another controversy or storm that's brewing in cosmology. I kind of expected a question, but I guess I'll get it next week. Thank you. Bye.